Okay, so in this class I want to look at a question that comes up quite commonly on our course, and this is an object moving with vertical simple harmonic motion, and there's a kind of a procedure. Step 1, we find the equilibrium position. Step 2, we show simple harmonic motion, and only after these two steps are completed will we look at further questions. So let's talk through this question, and then I'll go through a solution. It says a 0.25 kilogram particle hangs freely from a ceiling by means of an elastic string of natural length 2 meters and K equals 49 newtons per meter. So my spring constant here is 49 and my natural length is 2. It's released from rest at a point 2 meters below the ceiling. Shows simple harmonic motion. So what I'm saying here is I'm going to kind of ignore this bit until the end, until I'm actually going to start to find T and F and the other things. So I'm going to ignore that until after I've proved simple harmonic motion, and then I'll start thinking about finding the other quantities. So I'm going to ignore that 2 meters below the ceiling. So let me go through this question. First of all, I want to find the equilibrium position. So what I'm going to do, it's hanging freely from a ceiling by means of an elastic string. So if I draw the force diagram here for this particle, what will the force diagram look like? Well, it's hanging from the ceiling, and it's going to have a force acting downwards and a force acting upwards. Now, the force acting downwards is the weight of the particle, which is its mass, 0.25 multiplied by g. Now, I'm actually going to work out what that is. That's just a quarter of 9.8. And that's just going to be 2.45. I'm getting rid of my g here just to make it a bit easier to work with. So it's 2.45 newtons of force pulling that downwards towards the center of the earth. That's the force on the object by gravity. But there will also be a force upward on the object by this elastic string. Now we're going to use Hooke's law. We know that the force by an elastic string is of magnitude. The force is equal to K times L minus L naught. Now we're trying to find the equilibrium position here, so we don't really know what the extended length is, but we do know K and L naught. So K is 49. We don't know the actual length it's being stretched to, and that's, if it's something moving around, that'll be changing, and then we're subtracting the actual length, which we're told in the question is 2. Okay, and again, if I just simplify that, that's going to be 49 times L minus 98. That's going to be my force acting up. Again, notice it depends on how long, what the extension is, the string is. The first thing I'm going to find with questions of this type is always going to be the equilibrium position. And in the equilibrium position, well, you're going to find that the force up is equal to the force down. The magnitude of the force up is equal to the magnitude of the force down. That's what the definition is. So 49 times whatever the length is minus 98 is going to equal to the force down 2.45. Okay, solving that, adding 98 on both sides, I'm going to get 49 times the actual length is going to equal to 98 plus this. That's going to be 100.45, and then just dividing on both sides by 49 will tell me that the actual length will be 100.45 divided by 98, or divided by 49, which works out to be 2.05. So what have we found? Well, we found that 2.05 meters below the ceiling is where the equilibrium position of this object will be. So if I have a ceiling here and I've got the string and I've got my object hanging here, if this is extended, if that distance from the ceiling down to my particle is 2.45 or 2.05, well then it just won't move. If I release it from that point, I hold it there and release it, it's not going to bounce up and down. It's just going to sit there. Because at that point, the force up will equal to the force down. And if the force up is equal to force down, there's going to be no acceleration. So if I release it from rest at this point, it's just going to sit there. That's why it's called the equilibrium position. Now we're told it's released from rest at a point 2 meters below the ceiling. I want to show simple harmonic motion. Again, I emphasize I'm ignoring the number 2 until after I show simple harmonic motion. I will say that if it's released from rest 2 meters below the ceiling, that's kind of above the equilibrium position. And what I'm going to do, instead of thinking of it as being 2, I'm going to think about that as just being raised some distance x above the equilibrium position. And I'm going to define my system to be up positive. So I'm moving it up a positive distance of x units, and I want to examine what's going on. Okay? And we know from our force diagram that the force up is always 49 times the actual length minus 98, and the force down is always 2.5. And I can work out, what that force is, because I will be able to establish what is the natural length. Well, if the whole length down here is 2.05 and that's x, well then the actual length of the string at that point will be 2.05 minus x. And so we have the actual length of the string being 2.05 minus x. So what I'm going to do is examine the net force at this stage. Okay, I'm going to examine the net force at this stage. We know that the net force is equal to ma. Okay, we know the mass of the object is 0.25. We know that times the acceleration is going to equal to the net force. I've said it's an up positive system. So that's going to be my positive force. That's going to be my negative force. So the net force is going to be 49 times the actual length minus 98. That's my up force. Subtract my down force at 2.45. So simplifying there, we get 0.25 times the acceleration is 49 times the natural length minus 98 minus 2.45, that's 100.45. So this net force depends on not the actual length, but we know that the actual length is 2.05 minus whatever x is. And so we know that L is 2.05 minus x. So I'm going to just substitute that in. So I'm getting 0.25 times A is equal to 49 times the actual length, 2.05, subtract x, subtract 100.45. And again, this is just really a linear equation. All I'm doing is 0.25 A, 49 times 2.05 is 100.45. Multiplying it by the negative x, that's minus 49x, minus 100.45. And again, that's telling me that 0.25A is going to equal to negative 49x. Dividing on both sides by 0.25, or multiplying by 4, will give me negative 196x. So, what can we conclude? We can conclude that the particle moves with simple harmonic motion, since the acceleration is equal to a negative constant multiplied by its position, okay, in relation to its point of equilibrium. So we've proven simple harmonic motion. Let me remind myself of the question. The question all the way back says find the period, find the frequency, and the first two times the object will be at 2.08 below the ceiling. So, what about the period? Well, we know the period is always 2 pi divided by omega. And we know that A is always going to be, if it's moving with simple harmonic motion, then A is negative omega squared times x. So we can see omega squared has to be 196. So omega is equal to 14. Therefore, the period of motion is equal to 2 pi over 14, which is pi over 7 seconds per period. Which means the frequency for this thing, well, it's just the reciprocal of that. The frequency is going to be 7 over pi periods per second. So it'll complete 7 over pi periods every second. It's about 2.2. So it's completing 2.2 full periods every second. And a full period in this case means what? Well, it means if it's been dropped from up here, it's going to go down past the point of equilibrium, down to its lowest point, and all the way back up to its highest point. That's one full period. It's doing that just over twice every second. On the first two times that the object will be 2.08 meters below the ceiling, well, the first thing I'm going to do is establish some kind of expression for position. To establish some kind of expression for position. And this is where I'm going to go back and think about where it's released from. It's released from 2 meters below the ceiling. It's released from 2 meters below the ceiling. So if we think about it, there's its equilibrium position. 2 meters below the ceiling will be 0.05 meters above that, because the equilibrium position is at 2.05 and the lowest point will be at negative 0.05 on my coordinate system, which is now positive. So to find an expression for its displacement, I know the amplitude, I know the value of omega, so I can come up with an expression for displacement. It's also been released from one of its extreme points, so its displacement is going to be its amplitude, which is 0.05. It's been released from its extreme point, so we're using cosine function, multiplied by omega, 14 by t. So that's my expression for position. The question said, find the position when it's 2.08 meters below the ceiling. Well, the equilibrium position is 2.05 meters below the ceiling. It goes from 0.05 above the equilibrium position down to 0.05 below the equilibrium position. We're trying to find t when s equals, well, s 2.08 meters below the ceiling. Remember, this point here is 2.05 meters below the ceiling. So if the ceiling is up here, that's 2.05. 2.08 will just be a little bit below that. How far below that? Well, it'll be 0.03 meters below that. 2.08 meters below the ceiling will be 0.03. So we're trying to find the displacement, or find the time when s is equal to 0.03. In fact, I should say it's negative 0.03, because this is an up positive system. Substituting in, therefore, negative 0.03 for s is equal to 0.05 cosine of 14t. Solving this thing, we'll find that cosine of 14t must equal to negative 0.03 divided by 0.05. That's negative 3/5 or negative 0.6, I think. So we're into solving an equation, a trigonometric equation, and you've got to be able to do these. What do? We start off with the reference angle. We're dealing with radians. We're also dealing with radians for all these. In fact, probably better off starting with the quadrant. You know, cosine, where is cosine? Negative. Cosine is negative in quadrants 2 and 3. So cosine will be negative in here, in quadrant 2 and in quadrant 3. The reference angle, well, we know that cosine, the reference angle, is always the absolute value of cosine of the angle. So it's going to be absolute value of negative 0.6, which is just 0.6. So the reference angle is going to be cosine inverse of 0.6. Again, you'll need a calculator for that. You're not going to be able to do that in your head. That's working out as about 0.9273. Okay, I might just keep the value in my calculator as an answer. So that's my reference angle in there and in there. Notice pi radians is there. So my two possible values for 14t, remember 14t is the actual argument here all the way around. In the first picture, that'll be pi minus the reference angle, or 14t is equal to pi plus the reference angle, and then dividing on both sides by 14 to find t will equal to pi minus the reference angle over 14, or t will equal to pi plus the reference angle over 14. And there's my value for t. I just have to plug those things into my calculator and solve. So pi minus that number divided by 14. So for the first one, I'm getting 0.158. My units here are seconds. Or in the second case, again, I'm just typing in pi plus 0.9273 equals, and divide by 14. I'm getting 0.291 seconds approximately. So the times at which it's 2.08 meters below the ceiling are those two times. So go back over that, practice it. There's quite a bit in there. It's a little bit long-winded, but there's nothing in there that you haven't covered and you shouldn't be able to do. Practice.